Yeah, thanks. Much more complicated. Actually, well, apart from the beginning, I'll use camera only if there are questions that require. Okay, everyone. The question is here, two questions. Why two? Because we are celebrating today. You won't see me anymore. I won't see you anymore. I thought you would celebrate. Anyway, so let's celebrate with two questions. Okay. Or let's mourn with two questions. So you have an open loop system, K over S plus 1, S minus 2. And then you have a closed loop system, assuming that H in the feedback branch is equal to 1. So closed loop equals open loop over 1 plus open loop transfer function. So first question is the open loop system stable or not? No. Okay. Let's see. We know how to check stability. We check where the poles are. So we have one pole at -1. The other pole at +2. So why is this unstable then? Both poles are on the real axis, but because one is positive. The fact that they are on the real axis means only one thing, that we'll have exponential behavior, non-oscillatory. Apart from that, you look whether all poles are on the left-hand side. It takes only one pole to be on the right-hand side to make the system unstable. And that's the case here. So just in case, if you separate these two poles into two subsystems, this one will give you a response like this. So exponentially decaying curve. But this one will give you a response like this, because here you have e to the power of plus 2t. Here you have e to the power of minus t. Okay, so as the time approaches infinity, this stable component of the system becomes less and less relevant because the response is getting to 0. This one is the dominant one because the response is going to infinity, becoming bigger and bigger. So that's why no matter how many stable poles you have on the left-hand side, the one on the right-hand side will dominate the response. So that's why only one unstable pole will make the whole system unstable. So it's nothing to do. So in a different case, maybe when you have one pole here and one pole over here, this system is still unstable. So the fact that you have -5 here and +1 here doesn't mean that this -5 is stronger than +1. No. This one dominates the response. So only one rotten apple in the basket will ruin your whole basket. So only one unstable pole will make the whole system unstable. Okay, I hope you all knew that, but just a reminder wouldn't harm. But how about the closed loop system? So now when you apply a negative feedback loop, is your system going to be stable or not? Sorry, depends on K. Depends on K. Let's see. GC equals now to K over, let's expand this. So it's S squared minus 1S, sorry, minus 1S plus, no, it was 2. Okay, so GC equals K over S squared minus 2S plus 4. Down here you have 1 plus K over S squared minus 2S plus 4, which will be equal to K over S squared plus, so minus 2S plus 4 plus K. How stable this system is will depend on the poles of this new system, of the closed loop system. But you see that K will determine whether these poles are real or complex, whether these poles are on the left-hand side or on the right-hand side. So at this stage, there is nothing else we can say until we analyze all possible cases for k. And then we can say for these values of k, we have a stable system. For these values of k, we have unstable. And within the stable, for this subset of values of k, we have oscillatory. For the other subset of values of k, we have exponential behavior. Okay. Now, this is actually an introduction to our lecture today. So there are rules. There is a systematic approach to this. So rather than every time you get a closed-loop system, you struggle to determine the values of k that will give you stability or instability or exponential oscillatory stability or instability. We actually have a method that graphically and relatively easily answers all our questions. And in particular, this method becomes important if you have high-order systems. So this is relatively easy to do. You have two examples in set 6 similar to this. So find the range of values of k to get stability or whatever else. You just solve. You just make this equal to 0, the characteristic equation equal to 0, and solve it. But what if you have fifth-order characteristic equation? So let's do that. That is the lecture for today. Lecture 11. Okay, so the method, the technique that is used to determine where the poles are going to be as you vary k is called root locus technique. Just in case you are wondering what this acronym means, SISO stands for single input, single output. I'm not sure whether Dr. Kwok will cover multiple input, multiple output systems, but you may have, in reality, you have systems like that with more than one input and definitely with more than one output. So far we were lucky. We were dealing only with one input and only one output. Okay, so now if we have a configuration like this. So in the main branch, you have k times some sort of transfer function. We call this part of the system plant very often, therefore P. And also you have a negative feedback loop, so you have H in the feedback branch. Now, this k is actually the same as k we had a few minutes ago. This is the parameter we want to vary in order to see how stable the closed-loop system is. But otherwise, k times p of s is what we know as g of s, as the transfer function of the open-loop system, as we say here. Okay. So if g of s is the open loop, the closed-loop transfer function will be equal to this expression here, as we all know. How stable the new system is will depend on the denominator of the new system. So we create this denominator, this polynomial in the denominator with 0, and we solve the equation, where f of s is g of s, h of s. Okay. So we are going to look into this expression here. We are going to assume that h of s is 1, as we did so many times so far. But just remember that the open loop, if h of s is not 1, then the open loop transfer function equals to g of s times h of s. In other words, if you cut this line here, then the open loop becomes this times this. So the open loop transfer function gets multiplied by this. I mean, the main branch gets multiplied by the feedback branch, and that would be the open loop transfer function. So it is the more general case. But again, so far we always assumed h to be 1, so no problem. Still with the open loop transfer function, we know that it is a ratio of two polynomials, numerator and the denominator. But when you apply negative feedback loop, this new denominator is actually equal to the sum of the old denominator and the old numerator. So just if you check that, if you check what we did in this example, that's what you're going to get. So the sum of the two polynomials is your new denominator, which forms the characteristic equation of the new system, of the closed-loop system. Okay. And somewhere here, in the numerator, you have k. You have that parameter k that we will play with. Okay. So let's start with a very simple example. You have a second-order system, k over ss plus a, assuming h of s to be 1. Then characteristic equation becomes 1 plus g of s, which is 1 plus k over s plus a, or s squared plus as plus k equal to 0, characteristic equation. Now, as you can see, k, the value of k will determine the stability of the closed-loop system, will determine where the poles are. And when you draw the complex plane, so imaginary axis, real axis, you will find that if k equal to 0, you have two poles. When k equals to 0, one pole is at 0. The other pole is minus a over here. Then if you use some trial and error procedure, so if you make k just a little bit greater than 0, k equals 0.01, you will see that this pole will move a little bit to the left. At the same time, this pole will move a little bit to the right. And now you keep increasing k, 0.02, 0.05, 0.1, and so on and so forth, and you will find that these poles are getting closer and closer to each other. When k reaches this value, a squared over 4, then you get two identical real roots. K equals a squared over 4. And those two roots are equal to minus a half. So this is the case. So this is when they meet. They're kind of coming towards each other, and the meeting point is minus a half. That happens, as I said, when k equals to a squared by 4. If you increase k just a little bit more than that, you will get your first pair of complex conjugate roots. So now our poles are going to move away from the real axis. And as you keep increasing k, they get separated more and more. They get further away from each other and further away from the real axis. And if you get k equal to infinity, then you have those poles infinitely distant from each other, but still a pair of complex conjugate poles. Okay. How do we know that? Well, there are actually some rules in place, and most of them we are not going to prove, so we are just going to apply them, take them face value. Okay, the most general case, open loop transfer function is numerator over denominator. Both can be factorized. If you factorize the numerator, the roots of the numerator are called zeros. Now let's assume there are m zeros. When you factorize the denominator, then you get poles. And let's assume there are n poles in this case. This is the open loop transfer function. The closed loop characteristic polynomial, not the whole transfer function, but the denominator of closed loop will be equal to the sum of the old denominator and the old numerator, which is here. So the characteristic equation becomes equal to 0. I mean, characteristic equation is already equal to 0, but the characteristic equation becomes the sum of the denominator and the numerator, and that sum equal to 0. Okay. So here are some roots. If k equals to 0, the whole part here is 0. Then you're actually solving this characteristic equation, which is effectively the same as the characteristic equation of the open loop system. Okay, So when k equals to 0, the poles of the open loop are the same as the poles of the closed loop system, which is what we said here. If you remember, the original system, the open loop system, has two poles, one at 0, one at minus a. The closed loop system also has a pole at 0 and another pole at minus a. But that's true only when k equals to 0. Second rule, when k equals to infinity, then the poles become equal to zeros, to the zeros of the open loop transfer function. Some of the zeros may be infinity. We'll see later. Rule number 3, you will have some poles and some zeros on the real axis. In this case, back here, it's two of them. One at 0, one at minus a. So here's one pole, here's another pole. Rule number 3 defines which which parts of the real axis contain root locus and which parts don't contain any root locus. How you determine that? Well, you count all poles and zeros on the real axis. In this case, you have poles, you don't have zeros, and you have two of them. Those two poles divide the real axis into 3 segments. And we count from right to left, which is unusual, but that's how we do it. From right to left. So the first segment is from plus infinity to 0. Second segment is from 0 to minus a. Third segment from minus a to minus infinity. These 3 segments either completely belong to the root locus or they don't have root locus at all. Okay. You can't have half of the segment having root locus there and the other half not. Or you can't have 2 points within the segment and the rest not. No, it's the whole segment. Whole segment, yes or no. Which segment yes, which segment no, depends on how many singularities you have on your right, on the right from a given segment. By singularity, we mean poles and zeros as well. So this segment from 0 to plus infinity has no singularities on the right. So there is no root locus there at all, because you need an odd number of singularities. That's what you have here. So in this segment between 0 and minus a, you have one pole on your right. So this whole segment contains the root locus completely. And then this third segment has 2 singularities on the right, this one and this one. So there is no root locus between minus a and minus infinity. Yes? Yes, it is minus a half. We'll do this example following all these roots in detail. So the value of s is minus a half. Yeah. Okay, so that's rule 3. Rule 4. How many loci we actually have? How many branches? And that is determined by whatever is greater, number of poles or number of zeros of the open loop system. So in our case up here, no zeros, but 2 poles. So the number of poles is greater, and the number of poles is 2. Therefore, 2 loci, 2 branches. As we see here, there is one branch here, and the other branch down here, 2 branches. Rule 4. How many of those branches, how many of those loci end up at infinity? Well, that is determined by the difference between the number of poles and the number of zeros. Back here, no zeros, 2 poles, 2 minus 0 is 2. So both of those branches will end up at infinity. This one goes to infinity, the other one goes to infinity. They normally follow some asymptotes when they go to infinity. But in this case, this line is not only asymptote, this line is actually the root locus. So is the other line down here. Okay. Rule number 5, we need to define those asymptotes. Sorry, that was rule number 5. So how many of them end up in infinity? Rule number 6, define the asymptotes. And you will find that no matter how many asymptotes you have, they all intersect the real axis at the same point. So whether you have one asymptote, 2, or 12, they all intersect the real axis at the same point. That point is called the centroid. And the location of the centroid is given by this equation, which will be given in your final exam anyway, in the exam paper. But you need to take the sum of all poles minus the sum of all zeros and divide by the difference between the number of poles and number of zeros. That will give you the location of the centroid. Again, you will see this on some examples. What? Okay, but that's not enough. So you have the intersection between the real axis and all your asymptotes, no matter how many you have. You also need to find the angles at which the asymptotes intersect the real axis. Only then you have full definition of your asymptotes. So the angles are defined, phi A for asymptote, is defined by this equation, where Q is an integer, 0, 1, and so on, until you reach number of poles minus number of zeros minus 1. So 2Q plus 1 divided by the difference between the number of poles and number of zeros times 180 degrees. And then you vary Q from 0 until you reach, as I said, NP minus NZ minus 1. This equation, again, will be given in your final paper. Okay. So let's stop with 6 rules. There are more, but let's complete this example using these 6 rules. Then we'll introduce a few more rules. Okay, so back to our initial open loop transfer function. The characteristic polynomial of the closed loop transfer function is 1 plus GO of S equals to 0. Now let's apply these rules. So we don't know how many loci we will have until we apply all the rules, but at least the starting point of our root locus is the poles of the open loop transfer function. So it's 0 and minus A. So when k equals to 0, this is where we start. When k equals to infinity, this is where we end the root locus. Now, the number of finite zeros, there are no finite zeros. That means we have 2 infinite zeros. Okay, because the number of finite zeros is 0. There are no zeros. Okay, so when k equals to infinity, our locus is going to be somewhere at infinity. But we still don't know how it is going to get there. Rule number 3, segments of the real axis that contain the root locus. Here is one pole, here is the other pole. So 1 and 2, that's not the values of the poles, that's the number of the poles that we allocate to them. So first pole splits the real axis into this segment and what is on the left. Second one will add another division. First segment, from plus infinity to 0, has no singularities on the right. No poles, no zeros. There is no root locus here. This segment here has this pole number 1 on its right. So it's only 1. It is an odd number. So there is a root locus here throughout the whole segment. The last segment, from this pole to minus infinity, it has 2 singularities on the right. 1 and 2. 2 is not an odd number, so there is no root locus beyond this point. So the root locus exists only between these 2 points, between these 2 poles. Okay. Rule 4, how many loci? NP is 2, NZ is 0, so whichever is greater, 2, there will be 2 loci, 2 branches. Rule number 5, how many of them end up at infinity? The difference between NP and NZ is 2 minus 0 is 2. So 2 of them will end up at infinity. So if 2 of them end up at infinity, we kind of know there will be 2 asymptotes, because you go to infinity following an asymptote. But let's check that. So the centroid is given, again, using this equation earlier here. The sum of the poles minus the sum of the zeros. So the poles are minus a and 0, which is minus a, minus the sum of zeros, but there are no zeros. So minus 0. So that will give us minus a half. So this is a centroid. This is where the asymptotes, all the asymptotes, intersect the real axis, and minus a half. But what are the angles? Is it 0? Is it 90? Is it anything in between, or even beyond? Well, let's apply this equation. When q equals to 0, you have 1 np minus, np minus nz is 2. So actually we have 1 over 2 times 180, which is 90 degrees. So one asymptote is perpendicular to the real axis. For q equals to 1, we have 3 over 2 times 180. That will give us 270. So the other asymptote is also perpendicular, but from the bottom up. Okay. So back to this diagram here that I kind of guessed. So this is the first asymptote. This is the second asymptote. This is the centroid, minus a half. We just calculated that. Okay. Now, we still don't know everything about the root locus. Okay, where did we stop? Here. Okay, now, when we have a situation that 2 poles are approaching each other, when they meet, they separate and become complex conjugate. That particular point, when they meet, is called breakaway point, or you can also call it departure point, where the root locus departs from the real axis, or breaks away from the real axis. So we are now introducing rule 7. Where is that point? Where is that breakaway point? Okay. Now, once again, remember that this is the characteristic equation, g of s plus 1 equal to 0. Or you can rewrite this as k p of s h of s plus 1 equals to 0. From this equation, you express k. So k will be equal to minus 1 over p of s h of s. And then you find the derivative of minus k with respect to s, make it 0, and the solution of this new equation gives you the location of the breakaway point. We are not proving this rule, but once again, this equation, as simple as it looks, it will be also given in your final exam paper, just in case you're not sure whether it is k or k plus 1 or k minus or whatever. So it's d of minus k divided by ds. But k has to be expressed from this, or even better, from this equation. Okay, so in our case, if this is what we know to be the characteristic equation of the closed loop system, then minus k will be equal to s squared plus as. We need to find the derivative sy s squared, because when you expand this, you get s squared plus as. Derivative of s squared is 2s. Derivative of as is a. So solving this very simple equation gives you the breakaway point. And you find that it is also at minus a half. So you see, minus a half is a centroid and a breakaway point at the same time. It is a special case. In most other cases, this is not going to happen, that you have those 2 points coincide at the same place. So what is happening in this particular case, those 2 poles, as k grows from 0 upwards, those 2 poles are approaching each other. As soon as they meet, you keep increasing k and then start following straight lines all the way to infinity. Okay, so this is a relatively simple case. The only simpler case it would be a first-order system with one real pole. Okay, so let's try another example just to show you the breakaway point rule. Okay, so from this expression, you find minus k. So minus k will be equal to this. This polynomial is s cubed plus 3s squared plus 2s when you expand this. Find the derivative. So you will get 3s squared plus 6s plus 2 equal to 0. And then you solve that equation, and you get 2 values for the breakaway point. Which one is the right one? Well, let's check the system once again. If this is the open loop transfer function, no zeros, 3 poles. 1 at 0, 1 at minus 1, 1 at minus 2. Check the segments that contain the root locus, as we did earlier. This segment does not, because there is an even number of singularities to its right, even number meaning 0. This one does contain the root locus, because there is only 1, which is an odd number. This one does not contain the root locus, because there are 2 singularities to the right, 1 and 2, 1 and 1 more. That's 2, which is not an odd number. This one does. So from minus 2 to infinity, in all that segment, there is our root locus, because there are 3 singularities on the right, 1, 2, 3, which is an odd number. So the root locus exists here and exists here. But our solution for the breakaway point, 1 is where? About 0.4 something. So it is somewhere here, which is logical. You only have a breakaway point if there is a root locus there. So this is the right solution. Taking the other one, minus 1 minus 0.57 will give us a point somewhere here. This point is not valid. This point is not a valid solution, because you can't have a breakaway point unless you have a root locus. So you ignore this other solution. Okay. So when you get more than one breakaway point, have a look at what you have drawn so far. Okay. And see whether all those solutions, if you have 2 or more, which of them make sense, which of them don't. Those that don't, ignore them. And the final rule is departure points. So when you have the starting point of it's not the departure point, departure angles. So when you have a pole on the real axis, it's very easy to determine in which direction the root locus moves. It either moves left or right. Whether it moves left or right depends on which segment of the real axis belongs to the root locus, or contains root locus. So in this case, it's only natural that it moves to the left. So the departure angle is 180 degrees. For this one, the departure angle is 0, because this pole is moving to the right. This pole is moving to the left, so again, the departure angle is 180. But what if you have 2 complex conjugate poles? Then we can't clearly say in which direction the root locus departs. So there is a separate rule for that. Okay. So just imagine this is one of the poles, and we want to know this angle phi 5. So the departure angle, we don't know whether it is going to bend one way or another later on, but how does it depart? How does it leave? How does the root locus leave this pole? That's what we want to find. Okay, so you put into S-plane all poles and all zeros of the open loop system. Okay, so the assumption here is that you have one pole here, okay? So you have one pole here, one zero somewhere in between. And of course, if you have a complex conjugate pole, there should be another, the mirror image of it, on the other side. And then you draw the vectors. You connect every single pole, every single zero with the pole in question. Okay. Then the rule, again, another equation that will be given in your final exam. The rule is like this. You sum all angles with zeros. You sum all angles formed with poles and find the difference between the two. The difference equals to minus 180 degrees. This addition, minus 360L, where L is an integer, is there only to make sure that your angle is somewhere between minus 180 and plus 180. So you don't get something that requires 4 rounds plus 30 degrees. This will ensure 30 degrees. Okay, so back to this. The sum of all angles formed with the zeros, that's phi 3. So phi 3. Minus all angles formed with poles, phi 1. So minus phi 1. Minus phi 2, which is this angle here. Minus phi 4, which is this angle here. And minus phi 5, which is the angle of departure. So this angle is actually included. And all that equals to minus 180 plus this correction. Okay. So everything here you know. If you know the coordinates of all these poles, you can find these angles. The only angle you don't know is phi 5. So from this equation, you find phi 5. So here's an example. Open loop transfer function. Oh, G is missing here. So if G of S equals to AS over S squared plus B squared, then you will have 1, 0 when S equal to 0. And you will have two poles equal to plus minus square root of minus B. So you have a pair of complex poles. So you have a 0 here and two poles, one here, one here. You want to find in which direction the root locus moves from this pole. Left, right, and which angle. Plus 45, minus 30, 120, we don't know. So we will apply this equation here. So we'll connect this pole here with all other poles and zeros. There's only one zero and there's only one pole. Find those angles. So the angle corresponding to the 0 is 90 degrees. The angle corresponding to the other pole is 90 degrees as well. So the sum of all angles formed with the 0 is 90. Okay. The sum of all poles, with all angles formed with the poles is also 90. So sum of all angles with zeros is 90 minus 90 minus this angle we are looking for, phi P2. And that is equal to minus 180. So 90 and minus 90 will cancel each other. So we end up with minus phi P2 equals minus 180, or phi P2 equals 180. That means that the root locus moves straight to the left, 180 degrees. So from this pole, it moves to the left. The departure angle is 180. How about this one? Now we have a choice to apply this same equation for this pole, but it's not necessary. Root locus is always symmetric about the real axis. So whatever you have on the upper side, you will have on the lower side as well. So you simply know that this pole will also move to the left, will also follow 180-degree direction. Why there is a symmetry? Because you always have a pair of complex conjugate poles. Whatever you have on top, you will have on the bottom as well. Okay. Now we have all rules in place. Let's do another example now, unless you have questions. Okay, so here is our system. So the open loop transfer function has two parts, k s plus 2 and s plus 3 over s plus 1. So the open loop transfer function is simply equal to the product of these two. Okay. Rule 1, where are the poles of the open loop transfer function, or where are the starting points? S equal to 0, s equal to minus 1. Those are the starting points of our root locus. The finishing points are where the zeros are. So you have 1 0 here and 1 0 here. So minus 2 and minus 3. So you have 2 poles, 2 zeros. So let's see where they are. The poles are at 0 and minus 1. The zeros are at minus 2 and minus 3. Okay. Now we are not, okay, we'll see later. But we can now think about the third rule. Which parts of the real axis contain root locus? This part does not, because there are 0 singularities on the right. This one does, because there is one singularity on the right. That's this pole here at the origin. So the root locus will exist here between these two poles. It will not exist here because there are 2 poles on the right, and that is an even number. No root locus here. Here we do have root locus because there are 3 singularities on the right. 1, 2, 3, which is an odd number. So the root locus exists here between these 2 zeros. And finally, this segment has 1, 2, 3, 4. Therefore, there is no root locus between this 0 and minus infinity. So now we have 2 segments where the root locus does exist. How many loci, how many branches? That's the greater of the 2, NP and NZ, which is 2. How many of them end up at infinity? None, because 2 minus 2 equals to 0. So nothing goes to infinity. Therefore, no asymptotes. Why bother? You can try to get some funny angles or centroids, but you won't get anything or anything meaningful. Now, departure points. So if this is the open loop transfer function, then minus k becomes the reciprocal of the open loop transfer function. Find the derivative of minus k, so the derivative of this expression here. Hope you remember how it is done. First, leave the denominator as it is. Here's the denominator. And find the derivative of the numerator. S squared plus s. That gives us 2s plus 1. Then minus, leave the numerator as it is, and find the derivative of the denominator. So s squared will give you 2s. 2 plus 3 is 5s will give you 5, and 2 times 3 is 6. The derivative of 6 will be 0. So you have 2s plus 5. You also divide by the denominator squared, but this part doesn't matter, because if this is equal to 0, you are solving this. So the numerator equal to 0. And when you expand, when you sort out, when you cancel what can be canceled, you will end up with this equation. 4s squared plus 12s plus 6. The cubic term will cancel because you have s times 2s. That's 2s cubed. And here you have minus s here times s times 2s. So you have minus 2s cubed. So the cubic term will drop out. You end up with the second order equation. Again, something easy to solve. So you find that the roots of this equation are minus 0.63 and minus 2.3. And then if you look here, you'll find that both are placed where the root locus exists. 0.634 is here between these two poles. Minus 0.2344 is between these two zeros. So they are both valid breakaway points. Okay. Apart from, in this case, this is a real breakaway point. So two poles colliding and then breaking away, as we had in the previous example. That is a real breakaway point. This is a break-in point, if you wish. This is where these two poles meet and then move one left, one right. One towards this zero, the other one towards the other zero. This particular rule applies for both breakaway and break-in points. Okay. You just have to look into your root locus to see which one is the breakaway, which one is the break-in point. Okay. So eventually, you realize that poles, as you increase k, as k runs from 0 to infinity, each pole is looking for its own zero. They meet, they collide, they move away. Now, whether those zeros are infinity, so they go forever, searching for their zero forever, or they find their zeros, it doesn't matter. It depends on how many zeros, how many poles you have. But each pole finds a zero. It's like a fairy tale. In real life, it doesn't always happen. That's sad, but that's how it is. Okay, so let's continue with this fairy tale. Okay, so breakaway, break-in points. Okay. Now, how about a little discussion, then we'll have a break. Okay, I know it's about time. A little discussion. So which values of k will give us stability? Of the closed loop system. Okay, so as you change k from 0 to infinity, which values, which range of values for k this system is going to be stable? That should be a very easy question. The system is stable if all poles are on the left-hand side of the real axis. No matter what the value of k you have, you always have two poles, both poles, on the left-hand side. So whether one is here, one is here, or whether one is here or down here, or whether one is over here and the other one over here, they are always on the left-hand side. The only exception is when k equals exactly 0. So for any value of k greater than 0, this system is stable because the poles are on the left-hand side. That should be an easy question. The next one is a bit harder. When is our closed loop system going to be oscillatory stable? When it is going to be exponentially stable? Okay. So we don't know the values of k. We can determine that in a second. But as k increases from 0 until it reaches whatever value of k we have here, the system is going to be exponentially stable because you have two poles on the real axis. The only question is how far apart they are. But two poles on the real axis means exponential behavior. Once you exceed this value of k, then you start having a pair or complex conjugate. First, they are very close to the real axis. They keep moving apart, and then they keep getting back again. But all the while, between this point and this point, you have oscillatory stable behavior. Oscillatory because the roots are complex conjugate. The damping ratio is less than 1, greater than 0. But when you reach this point, you get exponential behavior again, because first you have two roots at the same point, and then they keep moving along the real axis, one left, one right, which is, again, exponential behavior. Okay. So the only question is what are the values of k that determine those ranges of values? Okay. So back to our characteristic equation. Now we know that in first case, s equals to minus 0.634, substitute, and then you get the value of k, 0.0718. The second case, when s equals to minus 0.344, you'll find that k equals 14. And now you have a full picture before the break. The full picture. When k equals to 0, you have neutral stability because you have one pole on the imaginary axis. For k greater than 0, less or equal to 0.0718, you have exponentially stable system. For k greater than 0.0718 and less than 14, you have oscillatory behavior. You have complex conjugate roots. And finally, for k equal or greater than 14, you have exponentially stable again. Okay, any questions? We'll do more examples after break. Yeah. Okay. Because s equal 2.1 is real. So you have one pole here, one over here. Okay, so that's exponential. But if you have s equal to minus 2.1 plus minus j something, that means they are here. Okay, in this case you have a solution. So I would rather ask that question in terms of k, values of k. So if k is greater than 14, then you have this. So this is, I know, k equals to 50, I know what. Okay? Then you have greater than 14, like this. Okay. So here, k equals to 14. Here, k equals to 0.07. When k is between 0 and 0.7, you have one pole here, one pole here. Because the poles are moving. This is k equal to 0, this is k equal to 0.7. So if you're gradually changing k, this pole is moving like this, this pole is moving like this. This is where they meet. This is k equals to 0.0. 0.08 means you have one pole here, one pole here. That's when you have oscillatory. And you keep increasing k. 10, 12, whatever, 13, 14, you're back. 15, your one is here, one is here. Yeah. Because k is equal to 0 here and equal to 0. K is infinity here and infinity here. No. Zeros, that's where k equals to infinity. So, yeah. So the root process goes towards zeros because you're increasing k from 0. And this is the path. One goes like this, the other one goes like that.
But in between here, like,
No. We're talking about the pole of the closed system. How they go? They go from this point towards this point. These zeros, they are zeros of the open loop system. They are defined by the open loop consequence. They don't move. Like the poles of the closed loop system, they start from here and they end here. So the arrows will always point towards zero. Yeah. task is they start from the port of the open loop. Open loop system. And they finish at the zeros of the open loop. They meet again, they separate. Okay, maybe I could say it is kind of clear, but not necessarily clear. Yeah, I will explain. I will just when you read the breakaway point, then the question is, you know that those not separate. They can separate under different angles. Actually, you can check it is always 90 degrees. It always lives under 90, and then it may bend one way or another.
But then this says it's only for 0, 0. Or 0, 0.
It's actually this is misprint. This is misprint. Okay. It's a misprint. The departure angles from the regular or return angle at the floating point is always 90 degrees. This 0, 0 degrees.
Is there ever a situation where life is crazy like that?
There is, yeah, there is.
But that's that one.
It's so specific, I don't think it will be fair to you. But it is possible
So you can always just shoot it correctly.
from the real life.
I'm just wondering, so, yeah. So is this also when k is equal to 0?
Yes.
So it's not
So-
only this and
Yes.
this.
So poles, because you have two poles of the open loop system, when k equals to 0, our poles of the closed loop system are exactly where the open loop. So it's k equals to 0, and then as you're increasing, they get together.
Then it goes around.
And but this is in both these points, k equals to 0.
So the zeros, k equals
Yeah,
to
the
0.
zeros of the open loop is k equals to 0.
Thank you.
It's exponential here to here,
Yeah.
and here to here,
Yeah.
and then imaginary,
Yeah.
exponential,
Complex. Yeah.
and then exponential, exponential.
Yeah.
Okay, got it. Thank you.
we are stuck. Okay, guys, let's move on. I think we had our 10 minutes, maybe 5 at least. This cable is a bit too short, I don't know why. Okay, so I hope we are happy with this example. So this example gives us not only the root locus, so not only those lines departing from k equal to 0, ending at k equal to infinity, but gives us, in case you didn't think about that, gives us the choice of which k we want to choose to get a particular behavior of the system. So do we... What's this now? Oh, because it's mute. Oh, because my microphone is not, I should be. I hope this will solve. Right. There is still hum. Okay, better. Now, depending on what you want from your system, you can select the value of k that gives you that particular behavior of the system. If you want exponential stability, you choose the value of k somewhere here, or possibly over here. If you want oscillatory behavior, then you choose a value of k that will give you the poles somewhere in this range. So actually, you have a choice. You have that flexibility. If, without the k, you only have one open loop transfer function. You find the closed loop transfer function, and you just look at the new transfer function and say, well, is it stable or not? That's all you can do. This way, as I said, you have a choice. Okay. Next example. Now we have the open loop transfer function here, k over s, s squared plus 2s plus 4. Rule number 1, find the poles of the open loop transfer function. One pole is at 0. But now you have two complex conjugate poles. -1 plus minus j square root 3. So 3 poles. Zeros, there are no finite zeros, so we say there are 3 infinite zeros. Which segment of the real axis contains the root locus? Now, there are no zeros, as we agreed. Okay, no zeros. When it comes to the poles, there is only one pole on the real axis, and that's S. That's 0. So one pole at the origin gives you 2 segments. One contains root locus, the other one doesn't. Okay? So if you look down here, ignore the rest of my artistic achievement, but just think, focus on the real axis. So you have one pole here. These 2 are complex conjugate. This segment has no root locus inside because there are no singularities on the right, which is an even number. This segment has only one singularity on its right, which is this pole here. 1 is an odd number, so the root locus exists all the way from 0 to minus infinity. So this segment does contain root locus. We'll get back a bit later to this drawing. Okay? So that's the segments of the real axis. How many loci? 3. Number of poles, which is 3, minus number of zeros, which is 0. 3. 3 loci. How many of them end up, sorry, 3, which is the greater between 3 and 0. 3 is greater. 3 loci. How many of them will end up at infinity? All 3. 3 number of poles minus number of zeros. Now, asymptotes, as we said, the centroid, there is only one centroid. So only one intersection between the real axis and all possible asymptotes. How do we find them? Let's get the sum of all poles, which is here, minus the sum of all zeros, but there are no zeros. So when you add these two things together, this and, sorry, one thing is wrong. 1 plus should be minus, another typo here. Plus minus j square root 3. So this one should be minus. That cancels the imaginary parts. So you have 0, minus 1, minus 1. That's minus 2 over 3. Okay? So the centroid is minus 2 over 3. Apologies for this error. So one of the pluses should be a minus. So this plus, for example, should be changed into minus. So the centroid is at minus 2/3. What are the angles? Angles between the asymptotes and the real axis. Here's the equation. When q equals to 0, then you have 1 over 3 times 180, which is 60. When q equals to 1, you have 2 plus 1, which is 3 by 3, which is 1, so it's 180. When q equals to 2, you have 5 over 3 times 180, which gives us 300. We can try again, and we'll get probably 420. But that is the same as 60. So we don't have to go beyond these three. And by the way, we already said that 3 loci will end up at infinity. That means we expect 3 asymptotes. Okay. No breakaway points. Well, how do we know that? Well, we can apply that formula for the breakaway points, which is here. And you will find that either that formula doesn't give you a solution or gives you meaningless solutions. What is meaningful, what is meaningless? Well, first of all, it has to be on the part of the real axis where the root locus exists. So if you have a solution which is positive, ignore them. Okay. But second, you can try to think a little bit. When k equals to 0, the pole is here. This pole is here. And then as you increase k, it is moving to the left. To have breakaway point, you need another pole to come from the right. So they need to meet and then bounce off each other. But there is no other pole coming to meet our only pole. So there is no breakaway point. So either use the logic looking into the graph or just apply the rule, find that derivative, and you will see there are no breakaway points. Okay. But departure angles, because now we have 2 complex conjugate roots, so we don't know in which direction. We have the asymptotes. One is 60, one is 300, and one is 180. So we know that at infinity, this pole will join this asymptote. And this pole will join this asymptote here. This pole obviously is joining this asymptote. That's kind of clear. We don't know how it starts. Maybe it goes like this, make some funny loops. So we want to find this departure angle here. Okay. So departure angles. So we need, if you want the departure angle from this pole, we need to connect it with all other poles and zeros. But there are only 2 other poles. One is here, and the other one is over here. The angle here is 90, okay, because they are complex conjugate poles. They have the same real part. So this is 90 degrees. This one we can find it is 120. Why? Because this angle is actually inverse tangent of square root 3 and 1. Okay, because this length is square root 3, this is 1. How do we know that? Well, we found these poles to be -1 plus minus j square root 3. So the imaginary part square root 3, real part is 1. So just a basic trigonometry. 1 square root 3. So tangent of that particular angle is square root 3 over 1. Or inverse tangent gives us the angle, 60 degrees. Okay. So now, some the sum of all angles, sorry, 60, but 60 degrees is this part here. 60 plus 90 is 120, because we are measuring this angle from the positive real axis. So therefore, it's 120. Now, apply the equation. The sum of all of angles formed with all zeros, there are no zeros, minus the sum of all angles formed with the poles. So you have 120, and then you have this angle, I'm not showing it here, which is 90. And plus phi 3, plus the departure angle here. That is equal to minus 180. So find that phi 3 equals to minus 30 degrees. So the root locus departs at minus 30 degrees and then joins the asymptote. Okay. And using the rule of symmetry, this pole has to depart at plus 30 degrees and then join this asymptote down here. Because remember, the root locus is symmetric about the real axis. Okay, before we introduce the last and final rule, let's again think about the stability of this system. So which values of k will give us which kind of stability? When k equals to 0, we have a neutral stability because we have one pole on the imaginary axis. As soon as k becomes greater than 0, this pole moves to the left. So this pole becomes stable. These two poles start moving to the right. So you have a stable system, but oscillatory stable because of those two poles giving us oscillations. So you have an oscillatory stable system. The problem here is that if you keep increasing k, then at some point you are going to cross into the unstable region. So these two poles, complex conjugate poles, will become unstable. Now, it's very important to find the value of k when that happens. So if you don't want your system to be unstable, you have to carefully watch the value of k. So you need to find that critical k that gives you instability. Okay, you already see, but let's see how it is done. Well, there are two ways. One way is using so-called Raoult or Raoult-Hurwitz criterion. Again, something we are not going to prove. We are just going to believe it is true. The other way, if you think about it, get back to the characteristic equation and make S equal to j omega. Because at this point, there is no real part is 0. So S equal to j omega and solve for omega. Okay. I will introduce this one. In the exam, you will never be asked to specifically use this method. Okay, so you don't have to use it. But it's just my duty. I'm required to show you this. Maybe you will love it. Very useful when you have, once again, when you have high-order systems. In your exams, you don't expect high-order systems, do you? Well, I don't. So that's why, this method may not be terribly relevant to your exam, but it is relevant for, practicing engineers. So now, your characteristic equation, again, is g of s plus 1 equal to 0. That can be expressed as one polynomial equal to 0. And that polynomial can be rewritten written in this form. So if the order of polynomial is s to the power of n, if the order of polynomial is n, then you have a naught, a1 up to an. You have coefficients multiplying each power in s. So when you create, but remember, you have to start from a0, then a1 up to an. Then you form a matrix like this. Sorry. I don't know whether this is dirty or what is happening. Okay, so first of all, there will be n rows of this Raoult matrix. First row contains A0, A2, A4, A6, depending on how many you have. Second row contains A1, A3, A5, okay, from this original polynomial. Now, you need to form all other rows by yourself. B1, B2, B3. B1 equals to, now, product of these two coefficients, A1 times A2, minus the product of these two, A0 times A3, and all divided by A1. That will give you B1. B2, you have product between this one and this one, A1 and 4, minus A0 and A5, again divided by A1, and so on and so forth. Now, C1, now you multiply these two minus these two divided by B1, and so on and so forth. Now, you will see as you go down D, E, F, and so on and so forth, that those rows become shorter and shorter. Because once you run out of coefficients here, you have 0, 0, 0, 0, 0, 0. So eventually you have something times 0 minus something else times 0, which will be 0. So you will have more and more of those equal to 0 and less equal to something not 0. And it will end at the nth row. Okay. So this is an example, so a little digression here. Sorry, it's not a digression, sorry, back to, this was digression. So back to our system here. So the characteristic equation of the closed loop system is s cubed plus 2s squared plus 4s plus k. So it is down here. S cubed plus 2s squared plus 4s plus k, that is equal to 0. This is A0. A0 equals to 1. Then this is A1. A2 is 4. You put 4. There is no A4, so it's 0 here. A1 is 2. A3 is k. There is nothing else. Now, this element here will be equal to this product, 2 times 4, minus 1 times k, divided by 2. So 8 minus k over 2 is given here. Next one is 0, because you have 2 times 0 minus 1 times 0, which is 0, divided by 2 is still 0. So we don't worry about that. And finally, this one will be equal to this product, b1 times k, minus 2 times 0, which is not there, and then divided by b1. So you only get k. Now, the Routh-Hurwitz theorem is that when you look at this first column, if all these terms are of the same sign, if all these terms are of the same sign, either all positive or all negative, the system is stable. But if you have a change in sign, that means you have instability. That means that for the system to be stable, because 1 is positive, 2 is positive, this has to be positive, and this has to be positive. So, when does your system become unstable? When this becomes negative. Okay? This becomes negative when 8 minus k equals to 0, or when k equals to 8. So if k equals to 8.1, this term is going to be negative. So that's how we know that k equals to 8 at this point. So this is a very important piece of information. If you don't want your system to be unstable, you have to keep k less than 8. Okay. And you will also find when you get back here, back here to the characteristic polynomial, then when k equals to 8 and you try to solve for s, you'll find that s equals to plus minus j square root, plus minus j times 2. Okay. We didn't show that, but you'll find that omega equals to minus 2 and equals to plus 2 here. Okay. I'll leave that to you to check. But this is actually what we really want. So the change in sign means a switch from stability to instability. You also have a potential change in sign here when k becomes negative. So in case the k is negative, but that's not the case with the root locus, you also have instability. So back here, you see that when k equals to 0, you have the boundary case between stability and instability. Okay, but this is kind of a special case, more theoretical than anything. Okay, so I'm going to leave this to you. So apply the Raud-Hurwitz criterion and find how many unstable poles this system has. Also, you have this fifth-order system. Why do we have such high-order systems? Because that's where this Raud-Hurwitz criterion really makes sense. Because it's very hard to factorize this and find the poles that are positive and poles that are negative. Now, in this case, you may find yourself in a position to divide by 0. So instead of 0, just take a very small positive number, very small, close to 0. Otherwise, you won't be able to apply. Then I will also leave this to you to practice. So draw a root locus of this particular open loop system, and then do the same for this particular open loop system. Okay. Any questions? If not, we'll finish a bit earlier today. I may see you in week 13 for revision, but that depends. I will have to talk to Dr. Kwok. If he doesn't need all 3 hours, then you will see me. Otherwise, good luck in the exam. Thanks, but you haven't seen your marks yet, so please. Yeah, thank you.
I was just curious, when you had the diagram of...
Oh, maybe I should keep it.
sorry, yeah.
No, okay.
It was of the root locus where it was passing the imaginary axis.
Yes, yes.
Yeah. I was just wondering what the significance of the departure angle that you had of 60 degrees.
Oh, no problem, thanks.
What was the significance of the point that you did the departure angle from? Because it wasn't at K, it was 0, the pole, it was...
No, it is the departure angle from the pole.
How come it's from here?
Oh, no. Oh, no, this is the angle of the asymptotes.
Yes, so
So the asymptotes form these angles. So,
Yes.
so to define the asymptote, I need to know the centroid, and I need to know the angle.
Of course, yeah,
No.
okay.
Yeah, sorry, I'll remove it. Oh, okay, so that was the question.
Yeah, that was it. Thanks.
Yeah, so they were doing like
Your consultation time still there?
Yes. If I don't teach, it doesn't mean I died. You know? This course occupies a lot of my time, but doesn't mean it's my life. So even when I stop teaching, I still exist. Same consultation time. So.
is it our final exam we'll assess some materials about before the exam? I mean for this part.
I don't know. I mean, you still need to know what poles and zeros are. You still need to know stability. You know, this damping. You know, oscillatory behavior means damping less than 1. Exponential damping greater than 1. So it's hard to say, okay, now forget everything. Are you done mid-semester? Forget everything, because there are so many things that are still relevant. You know, just when I do this, I assume you know that real rules means damping greater than 1. You know, but you can't separate it.
But like it will more relevant than materials after the exam, is it?
Sorry.
I mean in the final exam.
Yes.
So it will more relevance about this
Root
stuff.
locus will probably give you most points. I would have one question in final exam. Dr. Kwok, I think you have to see with me. In my question, the largest part is root locus. But there will be obviously other parts. There will be obviously steady state error and a little bit of other things.
Who's our lecturer?
Dr. Kwok.
就是
No, you will see him. Well, actually, not next Tuesday. Well, first of all, we have a break. Then Tuesday is a public holiday, so you'll see him on Friday, 2 weeks. 2 weeks, right? But you still have tutorials. Again, not on Tuesday. Next week. Yeah, you have this Thursday you have tutorials. No, Tuesday week 8, 25th. It's the week 8 Tuesday is a public holiday, so you don't have tutorials then. And you don't have this lecture. It's a bit unusual. Can I close this? Are there any questions on
No, no.
Oh,
Yeah, yeah. One of the best Mac lectures that I've
okay.
had.
Thank you, guys. Thank you. Okay. Well, we'll see. Good job will be measured with your mark. I hope so. Yeah, thank you, guys.
Don't get higher mark for saying that.
No, I don't even know their names. You can't say that I know your name.
You know my name.
Well, I can figure out from the list of students which one is yours. I know it's towards the end of the list. Is it Y or Z? I'm not sure.
Y.
When I see it, I know it, but I don't know. Sorry. No problem. Oh, thank you.
See ya.
See you later, guys.
Thanks, Sarah.
Oh, okay, okay. Yeah. Well, it's really cool. I mean, first of all, I have no idea how big the class is going to be next year. So, and I will try to keep, maybe one, I should say that. I will try to keep the current demonstrators if they are still available next year. And then possibly have more, if depending how big the class is and how many. I know I'm losing one, definitely. The one I would like to keep, but she submitted her PhD, so she will be gone next year. So I'm definitely losing one, maybe 2 or 3. I don't know. And also depends how big the class is going to be. Am I going to run everything the same way I'm running this? So there are so many unknowns, I can't tell you anything. Feel free to contact me. Somewhere in December, January. Feel free to email me. And then depends on how many more I need and how strong the competition. Like applying for a job. If I need 2 people and you are the only one applying, you will get the job.
Yeah.
But if I need 1 person and 5 of them apply, then I can't promise. But that's all. But thanks for your interest. No, that's okay. I just log off and I think. Yeah. Forgot to say what you told me. Okay. Yeah.
So in terms of like the shape here, in other words, we didn't talk too much about what shape it was.
That's right. Because for you guys it's enough. So if you draw a circle, that's fine. If you draw an ellipse, it's fine. So it's nice. So there are no corners. I can say that, but you see from each of these we drew, they're all nice and smooth curves. So there's no sharp corner. If you want to know exactly, I think you will have to go point by point. So you keep changing the case. Good news is MATLAB has a built-in program, root office. I know exactly how it ties the command, but there is a function called root office. So it will give you the exact shape. In the exam you don't have it. You have to sketch it. But as I said, it's good enough. Something, any nice curve and two symmetric curve, that's asymmetric possible with a free hand draw.
Can I just ask one more?
Yeah.
So for this
I
class,
said, I am actually still in class, so why not?
so just this one, so for us we had 20 days and 5 minutes.
Yeah.
For a question like this, all these are going to be real life. They're all going to
That's right. So the question is, so you just check are they all positive or all negative? Because it's the change in sign that determines instability.
So if it's like positive, positive, negative, negative, then it's only one.
That means one fall on the right hand side. One.
Yeah.
But if you have positive, positive, negative, negative, positive, positive, that means you have 2 changes in sign, so 2 falls on the right hand side.
It doesn't have to be a polar, right? It would just be like,
No, the root, okay. In this case, it's a polynomial, so it's a root. Okay, no, you do keep greater than it. No, both of the causal both of the causal construction. One is okay. We are quite happy with this. We're happy to have as big k as possible, but these two become unstable.
Wait, so we're graphing, so this is graphing A from open.
So these are the locations of the cause of the causal system. They will depend on k. If you remember the very first thing I asked you, okay, this is the open loop.
Yeah.
Okay, the closed loop system, the cause of the closed loop system depends on k.
Yeah.
And now we found that as you vary k from 0 to infinity, where the poles of the closed loop system are. It actually follows some smooth lines, as you discovered today. So this root locus or locus is Latin for location, place. But the way we use it is locus means all possible locations.
Yeah, yeah.
Okay, the sound. So all possible locations from 0 to infinity, that infinity. All possible locations, all the closed loop. Yes, but these three are points of the open loop.
Okay, so
So
these.
you have an open loop system, and it has its poles. Now you ask yourself, if I close the negative feedback loop, where are my new poles going to be? And depends on k. They will be anywhere between here and here and here. So these are poles where the poles of the closed loop system are depending on k.
Yeah, okay. So in this case, if A was 8,
Yes. So you have a neutrally stable, so you have two poles right on the imaginary axis. You have oscillations with constant neutral oscillations.
oh, so okay, so like you just sum K, so that would be the poles of the.
That's right. If k is 8, the poles of the closed loop system will be neutrally stable.
Exactly.
Yes. That's what we calculate.
So that was like cool.
Yeah.
Very cool. Thank you.
So, as an engineer, if you want to choose k, don't be fooled by this one, because normally you would like this one to be as far away as possible. Because the time constant is lower. This is quicker and quicker.
Yeah.
Okay, but these two are getting less and less stable until they become unstable. So you have to make